All right, good afternoon, everyone. Let's get started with lecture 11 for EfficientML.ai. In today's lecture, we are going to learn about TinyEngine and also parallel computing. This is a new chapter, hopefully pretty exciting. So the plan will consist of 3 parts. We are going to learn today. We are going to first talk about Edge AI, like what are the hardware platforms, what are the characteristics of those Edge AI and also IoT devices, why deploying them is resource constrained and why they're challenging. And to solve those challenges, we want to exploit as much as possible the available computational resources. So we are going to introduce parallel computing techniques, which applies not only to TinyML, but also large language model. This is very crucial for our Lab 5, where we are going to implement the Llama 2 7 billion parameter Llama 2 model on a laptop. We are going to use these techniques, including loop optimization, multi-threading, CVD programming, and also the CUDA programming. Very useful techniques to learn about those system techniques. So for machine learning researchers, it's very crucial to learn about those systems implementations. The algorithms change every day, but those fundamental systems implementations and principles would be quite helpful no matter how the algorithms evolve. And next, I'm going to introduce some inference optimizations like image to column convolution, in place depth-wise convolution, memory, what is the efficient memory layout, and also the Vinograd convolution. So what's the difference between what we learned so far and these optimization techniques? Like the techniques we learned so far, like pruning, quantization, neural architecture search, they change the algorithm, right? The neural networks we run, they are different. They are either pruned or they have been quantized to low precision, or we find a completely new architecture or the still existing architecture. But these techniques, these optimization techniques, they are functional preserving. They're mathematically equal. They are just systems. From the system's perspective, they are the optimizations. But from the algorithm's perspective, they are still the same, not changing the algorithm. So that's the difference in the relationship between what we learned so far and the new concept we are going to learn. Okay, so introduction to Edge AI. There are so many edge devices like smart homes, smart robots, vehicles, office, different kind of smart machines in the office, in the hospital, radio transceivers, vending machines, home appliances. So from this cloud computing to edge computing, this is showing a challenge about the amount of resource we have from like a cloud GPU to a laptop, to a mobile phone, to a microcontroller. So for the cloud GPU, the H100, NVIDIA H100 is the state-of-the-art GPU, which has 80 gigabytes of memory in each card, and the server can easily have tens of terabytes or even hundreds of terabytes of storage. Like the server in our lab, we have like 24 terabytes of storage, pretty big. The computing power is almost 2,000 TOPS per second. It's also pretty energy consuming. Like each power socket that is 208 volts, 3-phase, 50 amp, pretty thick electric cable that can host only 2 A100 GPU nodes, two nodes of A100. And if it is H100, a node like this, it can host only 1 H100, which is huge amount of electricity. So in contrast, the laptop, you have like between tens or 100 gigabytes of memory. The largest Apple M2, which is the M2 Studio, Apple Studio, I believe, has 192 gigabytes of memory, also pretty big. Several terabyte, 1 or 2, up to 8 terabytes of storage, 30 TOPS per second of computing power. Actually, this is a lot of computing power in a laptop, and also pretty big memory. It's actually even larger than a single GPU memory. as you can see, as you can find in the largest M2 Ultra Apple Studio. The latest phone mobile CPU, for example, Qualcomm S8 Gen 2, 8 to 24 gigabytes of memory, several gigabytes, maybe 100 or 200 gigabytes of storage, 36 teraops per second, which is actually plenty of compute as well. But for these IoT devices, very scarce of memory, only 320 kilobytes of memory here. Previously, we were talking about gigabytes. This is not megabytes, this is kilobytes. And here is the storage available on the flash that is read only, which can only store the weights, not the activations. This is read only 1 to 2 megabytes, and only like a few hundred million ops per second. Several orders of magnitude different from here, like several teraops per second. So this is a detailed breakdown about different components in a ARM Cortex M7 microcontroller on the first row versus the MacBook Pro, the second row, and this is difference in the ratio. Number of CPU cores, 1 to 20 times different. The clock rate for the microcontroller, only 200 megahertz versus 3.2 gigahertz. That's another 15 times difference. No GPU, no neural engine core on the microcontroller. And the L1 cache size, 320 kilobytes versus only 8 kilobytes on the microcontroller. And the microcontroller doesn't have L2 cache nor L3 cache. And the memory capacity, 320 kilobytes versus 64 gigabytes. That's like 200,000 X difference. Storage, 8 terabytes versus 1 megabyte. That's a lot of zeros I cannot read. There's so much difference. But how do we squeeze neural networks into such tiny devices? That's a big question for us. So therefore, that motivates us to exploit the available resources, very scarce, very little, how to best utilize those available resources in compute and also in the memory to do as much work as possible, right? And also, when we are having a lot of GPU cores, a lot of computing resources, how do we exploit them to parallel computing, do multiple operations at the same time to make our workload run faster? Therefore, the techniques we are going to learn is the parallel computing techniques, okay, which are going to help not only tiny machine learning, but also this big machine learning, right? For big machine learning models, there are plenty of room to parallelize our computing across different dimensions. So making parallel computing pretty important for both inference and also training. So here we are going to introduce 4 very widely used parallel computing techniques for both TinyML and big and large ML, including the loop optimizations, since these tensors, naturally you have many loops, no matter if it's convolution or if it is matrix multiplication. SIMD programming, multi-threading, and also pull-down programming. Within loop optimizations, we are also going to cover 3 sub-concepts, including the loop reordering, loop tidying, and loop unrolling. And let's learn them one by one, starting with the loop reordering to optimize the cache locality by reordering the sequence of loops. So let's see a simple matrix multiplication. Simple matrix multiplication, n by n times n by n matrix. And the naive implementation consists of how many loops? 3 loops. Then ijk, so Cij plus equal to aik times bkj. If you use that naive implementation, what is the order that we access the memory in matrix A and B? This is matrix A. When we do aik, okay, so K is the inner loop, So we're going to do it in this order. That's pretty good. Assume the data is stored in a row manner. So this is our contiguous memory access. B, we're using BKJ. K is in the loop, so we're going to loop in this order. Right? So B00, B10, they're actually not continuous, not contiguous in the memory. So the locality is very poor for the B matrix. Can we reduce the cache miss and improve the data locality by changing the order? So originally it's IJK. What about IKJ? What will happen if we do that? What will be the order for B if we change the order from IJK to IKJ? Yeah, in a row-wise manner, right? So rather than this way, we're going to do B in this way, right? So B is K and J, and we do K first, and J last. So B will also have this row-wise access pattern. What about C? Is C getting better or getting worse? If we change from IJK to IKJ, C will have a worse locality because previously, after looping through the J and K, C has a pretty fixed. We just calculate the same C, IJ within the K, right? So after calculating one component Cij, we move to the next component Cij and loop over K, right? So C has pretty good locality. But in this way, J becomes inner loop, I is the outer loop. So C no longer have its best locality, right? So there's always the trade-off. There's no best of both worlds for A, B, and C, right? You have to do some sacrifice. But overall, in this way we can effectively accelerate the matrix multiplication. So previously it's taking 24,000 milliseconds using our first implementation on the left. And using the loop reordering from IJK to IKJ, we get 12x speed up, very reasonable speed up, measured on Xeon 4114 and server grade Intel CPU to only less than 2,000 milliseconds. No hardware change, just change the loop order from IJK. Now it's IK and J. Now we immediately get an order of magnitude speed up by having the better data locality for the B matrix. Okay, I'll give you 1 second to compare this code versus the code here. Notice that we define the local variable here, AIK, to avoid the frequent memory access inside the loop. So rather than having AIK here, since it's the same, irrespective of what J is, we define it in the front. Okay, so that's loop reordering. Let's now talk about loop tiling. Okay, to reduce the memory traffic, memory access by partitioning the loops iteration space. Why do we need partitioning? So we have limited resource, very limited cache size, like microcontroller L1 cache size, only 8 kilobytes. Okay? But the matrix can easily get much larger. Then what do we do? So in this case, assume dimension of ABC is n by n, so they're all of dimension n by n. So how many elements do we need to access for B? Pretty big, n squared. Right? That's the memory footprint we have to touch in order to cover the whole B matrix. What if the cache is smaller than that? So we will suffer from a cache miss because the data in the cache will be evicted before reuse when the B matrix is much larger than the cache size. Then we can do loop tiling, which can partition the loop iteration space rather than loop over from 0 to n, we can have a subspace each time. And each subspace can fit in the cache. And we ensure the data stays in the cache until it is fully reused. So let's see, how do we do that? This is the conventional way, ijk n, and the footprint is n squared. What do we do here is rather than 3 for loops, now how many for loops? We have one more. We have four for loops. For j, we broke it down into 2 for loops. Okay, the first one step size is 1. The second one step size becomes t. Okay, t is the tile size. Tj is the tile size for j. Okay, so within this range, the footprint will be only n by tile size rather than n by n. Okay, so we carve out, partition, or block a small block of this B matrix so that we can have a smaller memory footprint. We only work on the first n by tile size of B matrix. Exhaust everything, all the elements here, before we move to the next block, since this is in the outer loop. So the number of elements will be accessed for the B matrix will be reduced from n squared to n times the tile size in this way. What if that is still too big, right? N can be pretty large, so n times the tile size can still be quite big. So rather than these 4 for loops, we can do another level of tiling. Okay, so here we have 5 for loops. We not only tiled the j dimension, okay, the j dimension, but also tiled the k dimension. Okay, so this is t tile size of k, and we put that in the outer loop where the step size is not 1 but tk tile size of k. So effectively, we tiled the B matrix from n times the tile size to tile size times the tile size. So finally, we can make it even smaller, okay, from n tile size to tile size square. And similarly, the number of elements in A is reduced from n squared to n times the tile size. Is that solving all the problem? Actually, there's still n. If the size of the matrix is large, the memory footprint for A can still exceed the tile size. So we can do another level of tiling. Okay, so previously A is n times the tile size. Now we want A to be also tile size square. How do we do that? Rather than this is the 5 for loops, we tile not only j, k, but also I, so that we can have 6 for loops. So here we have the tile size for I, and here we skip. The step size becomes ti. So for all 3 components, for 3 for loops, we tile each one of them. Therefore, the number of elements accessing A becomes tile size square, and similarly for B and C, rather than n squared, now it is tile size square. And we started from this 3 for loop. Now we ended up with 6 for loops. And the tile size can be determined according to the tile size. The cache size, make sure the tile size is smaller than the cache size, so that we can fit the working set of data into the cache. We reuse the data in the cache as much as possible, therefore reduce the cache miss. So in several scenarios, if we have multi-level cache, and sometimes we also need multi-level of tiling to support the multiple level of caches. So here we have 6 for loops, okay? And here we can further for tile size, the second level, starting with the J, okay, the second level of tiling. So that if you see from here, okay, the original memory footprint seen from this for loop is tile size square, but one more that becomes B times tile size. But after tiling, another tiling for J, second level, that reduced from times tile size to tile size 2 times the tile size 1. Okay, so this is trying to fit this working set in the second level of cache and this working set in the first level of cache. So when you have the multiple level of cache, you also want to have multiple level of caching of tiling. Each level of tiling fits the size of each level of cache. So let's see in the real world, what is the measured speed up using this tiling, using the 6 loop, 1, 2, 3, 4, 5, 6 for loop to tile this matrix multiplication. But naive implementation, 24,000 milliseconds. And after loop tiling, it becomes 20 times faster, 19 times faster, only 1200 milliseconds. This is amazing, right? So we prepared all these code for you to try on your own laptop. Actually, we prepared the example code on each slide on the top right corner. You can click that link to compile the code to see the loop orders, try to play with different block sizes, and it's highly possible you can get even faster inference speed than ours. And we also have such exercises in Lab 5, so giving everyone an opportunity to play with it.
As you change the block size, clearly there has to be some range of performance levels. It's a relationship to that with block size. You take it all the way to N, you're getting back to the original base case. Have you never like plotted a curve to see if there's C patterns that are block sizes?
Yeah, that's a very classic exercise in David Patterson and John Hannes's textbook. There's such a plot. Actually, you can use that plot to determine the cache size, since you can imagine that is not contiguous. But at some point, the latency will suddenly jump as soon as the block size exceeds the cache size. The latency will suddenly have a bump because you can no longer fit that level of cache. So you can imagine the relationship between the latency versus the cache size is very bumpy. And the number of bumps corresponds to the number of levels of cache hierarchy.
So these we have a lot of loops. Why don't we? I guess even this is a question for the previous operation. Let's do it. Reducing for loops. Why can't we just reduce it to one for loop? We flatten our matrix and then we just have a second list instead of the indices. The actual positions, we just say that do the whole thing in one for loop.
Doing it in one for loop, that's actually the next technique, loop unrolling. We are going to unroll it to reduce the number of for loops, right? But those are orthogonal techniques. You still want to have the locality. You don't want to traverse the entire, just one dimension traverse it all the way to the end, but that will hurt the locality for the other dimension. But next we'll introduce loop unrolling.
In the multiplication, are A, B, and C different levels of the cache, or are they in the same level of the cache?
You want to put them in the same level of cache.
Right. So then, is it obvious why the fact that cache misses get worse in C and better in B is net positive and results in that 19x speed up?
Oh, so you refer to the question when we're doing loop reordering, we make the locality of B better, make the locality of C worse, right? But why the overall locality is better? So in that case, previously for every element of B, they are not contiguous. They differ by a row, right? But for C, we can do the reduction for one the entire row, at least for the entire row rather than element wise. So that's the trade-off. All right, so that naturally leads to our next discussion, loop unrolling. Can we reduce this branching overhead at the expense of the binary size? Let's see our familiar example again. Actually, the loop control add a lot of instruction and branching overhead, right? We have to manipulate the pointers ijk, and also we have to test if it is the end of the loop, to test if ijk is smaller than n. Okay, if it is smaller than n, then we branch back, otherwise we continue. So this branch prediction also incurs overhead in processors. Okay, so we want to reduce those overhead. Therefore, we can do loop unrolling to replicate the loop body by a number of times. And to have a trade-off between the binary size, since we're unrolling the loop body, we're going to see very quickly what that means. That actually increase the binary size, but we have the reduced overhead. Let's see example. This is without loop unrolling. This is loop unrolled by 4. We can clearly see the difference here. Previously, the step size is 1, but here the step size of k is 4. Okay, what does that mean? Every time we do k plus 1, k plus 2, and also k plus 3 within this loop. So for the program counter, the PC just PC plus 4, PC plus 4, PC plus 4. There's no branching instruction for that frequently as before. So previously, every time this sentence is executed, we have to test whether ijk is still in the range. Right now, we have 4 times less number of branching operations. So the arithmetic operations for pointers is reduced by 4 times, since we have manually unrolled the k plus 1, k plus 2, and also k plus 3. The number of loop tests also reduced by 4 times. Since we unrolled everything, now until here, do we need 1 loop test? However, the code size will be inside the loop will be 4 times larger. Okay, 4 times. This is compared with before. So let's see, in real world, we provided again on the top right corner. And now GitHub, we released the loop unrolling on the CPU. Okay, to speed up matrix multiplication from these 3 for loops. Okay, we still have these 3 for loops. We unrolled both the j dimension and also the k dimension. So in j dimension, we unroll it by 8. Okay, so here we unroll it by 8. And then unroll the k by 4. So k plus 1, k plus 2, and also k plus 3. And here we have both j and also j plus 1. So before unrolling 24,000 milliseconds, after unrolling 8,000 milliseconds. Feel free to try on your own laptop. This is hopefully easy to compile without dependency. You can immediately see a couple of times of speed up. And we are going to use this technique in our lab 5 to accelerate the Llama 2 running locally on our laptop. Okay, so far we introduced 3 techniques. Can we combine them together? Are they mutually exclusive? Right, they are not mutually exclusive. This is reducing the branching overhead, and these 2, reordering and tidying, they are improving the cache locality. We can actually use them together, which gives us a pretty large design space to combine all these techniques together. Actually, we give you some bonus point to try exploring this large design space to figure out the best reordering hyperparameters, the best tidying hyperparameters, and also the best loop unrolling hyperparameters. Like you can unroll by 4, you can unroll by 8, you can enroll by tool, you can enroll J dimension, K dimension, or both IJK dimension. What would be the best, right? And actually that depends on the hardware. Different hardware might prefer different strategies, which makes this a very interesting thing to explore. All right, after that, let's conclude this loop optimization and shift the gear to SIMD, another crucial implementation to accelerate for parallel computing using single instruction, multiple data. We want to perform the same operation on multiple data points simultaneously. Since deep neural networks is very easy to parallelize, lots of loops, lots of pixels, lots of tokens. You apply the same thing, same weight to different dimensions. So we can avoid those control overhead, those instruction overhead by applying the same instruction on multiple data to let them lockstep with each other. Before jumping into SIMD, we want to first review the ISA to give you some reminder for what we learned in 6.04 in computer architecture and computer system organization. Give you some warm up. So as you recall, what is ISA? The instruction set architecture. So that's the interface between the software and the hardware. That is the contract for the computer to abstract away those details for the programmer. Defining how the CPU is controlled by the software. And that is the interface for the programmer to interact with the hardware. And there are several examples of the ISA, several instructions, several examples of the instructions, including the add instruction, like adding two numbers together. Compare the numbers, which one is larger, smaller, compare with the 0. Jump to a certain location. And conditional jump, if the condition is met, then we jump to a certain pieces of code. Load word, load instruction to load from the memory to the CPU. Store word, store information to the memory. And also these I/O instructions to do input and output to a monitor, to a keyboard, etc. And there are two broader categories of ISA. One is the CISC, the other is the RISC. In CISC stand for complex instruction set computer, and the RISC stand for the reduced instruction set computer. Okay, so the CISC have many specialized big instructions. Like it's very widely used in the desktop CPUs like Intel x86. Well, RISC is usually applied to low power processors. It's usually smaller instructions, much shorter, much regular. I can do less amount of work in each instruction for the same amount of same program. We have to use more instructions here, but each instruction is more lightweighted. For example, doing a simple add operation like C equal to A plus B, the CISC may need only one instruction, like add ABC. It automatically fetch ABC from memory, add them together, and store them back in the memory. While in the RISC, we may have to break down into several instructions, like load A into the register 1, and then load B into register 2, and then add register 1 and register 2 together. The result, we store them in the register 3, and finally we store the register 3 to the memory location C. And we can tell the difference between RISC and CISC. The amount of work you do is more in the CISC, but the number of instructions you have to have is more in the RISC. So what is SIMD? Okay, single instruction, multiple data. So previously, like the example here, one instruction just operate on one piece of data. Okay, just one operand, A, B, and C. Okay, we are just doing for a single add operation. But tensors are actually parallelizable. Okay, so the A could be a vector, it could be a tensor. Okay, you can do, for example, here you can do a element-wise add for vector A and a vector B, rather than just a single entry A and a single element of B, right? So since they can be done in lockstep manner, can we just use one instruction like add or multiply? But we want to operate on multiple data. That's what SIMD stands for. Right here, a single instruction, single data is trying to multiply two 32-bit numbers A and B together. But using the single instruction multiple data, we can simultaneously operate on 4 IP32 numbers. Okay, so the register is no longer like a single IP32, which is 32-bit, but 4 IP32 numbers, which is 128 bits. So the register is much larger in the CMD. And we are doing the multiplication for 4 numbers, A0 times B0, A1 times B1, etc. And we store them into C0, C1, C2, C3. And that's the difference between a conventional single instruction, single data versus single instruction, multiple data. This is very common in modern processors. Even on microcontrollers, they offer such feature. For example, maybe not 4, but 2 elements can be done in parallel at the same time using one single instruction. So key feature, we introduced this vector registers. Like the register over there, it's 128-bit that can hold 4 IP32 numbers rather than 1 IP32 number. So that's the vector register. And also vector operation. Easy to understand. This is a vector operation operating on 4 elements or multiple elements independently. So with the CMD programming, we can increase the computational throughput. Only one instruction now we can operate on a much wider array rather than just one scalar, and improve the energy efficiency. Since in computer architecture, instruction overhead is actually not negligible. We want to try to avoid and amortize this instruction overhead across a larger amount of data. So now, before we jump into these details, let's take a break. And after that, we'll review the program and how do we write CMD programs. All right, let's resume our discussion about parallel computing and also CMD programming. And let's see a real world example. How do we use these CMD instructions to write some real programs to multiply, to multiply 2 vectors together. And here I'm going to introduce both the Intel SSE instruction and also the ARM's NEO instruction. So SSE is the CMD intrinsics or CMD instructions from Intel, and also NEO is the same thing from ARM. So here we are comparing the conventional single instruction, single data programming to do a dot product. Okay, and so here we are multiplying each element of A and B and added to C. And we have to loop it over the entire n dimensions in this array, which is 1 by n. Loop over AK and BK, sum it together, and also go through 0 to n. So that's the single instruction, single data version. What about the CMD version? This is the Intel version. This is the NEO version, the ARM version. Okay, so for the CMD version, so we no longer have to loop from 0 to n, but now we loop from 0 to n minus n divided by 4. Since each time we're computing on 4 entries, therefore we need 4 times less number of loops. And here we are loading A, loading B to the. And let's see what does those entries mean. So here, means multimedia, and load, mul, add, they just mean load, multiplication, and also the add. So this is loading from A and K times 4, because each time we are loading 4 elements. Okay, so that's why we have K times 4, and also load from B, also K times 4. And PS, what does that mean? It means packed single precision. Okay, so each number is a single precision, and we pack 4 of them together. After loading the two, we feed these 2 operands into multimedia multiplication, packed single precision to multiply them together. Okay. With neon instruction is very similar, just they have different naming. So here V stands for vector, not just a single scalar, but a vector. This load, multiplication, add, and this is the number of vector Q for quad word. So every instruction is dealing with four words together. So this V for vector, this is multiplication, this is quad word. Okay, 32 means each one is a floating point 32 single precision. Load A, load B, 32 bits per entry, and we have 4 entries, so this is quad word. And finally, multiply them together and add it to C. So this is comparison between the C programming and also the SIMD programming. In order for you to play with it, we also released the code on the top right corner. We give you the code for both x86 if you have Intel CPU, or the ARM instruction if you have a Mac CPU or Android or Raspberry Pi processors. Okay, so this is the Intel version. This is the ARM version of doing a matrix multiplication in the SIMD manner. We're going to see this in our lab 5. So as you can see, we have 4 loops. This is the same as before, but each operator, they are no longer a single number. There are 4 entries. So the register is 128 bits. Why 128? Because each number is 32 bits, and we have 4 of them at the same time. So every time all the register is of width 128. So here we initialize A, B, and actually we transpose B. Okay, remember in the loop reordering, if we don't transpose B, we have to do we can either transpose B or we do the loop reordering. They are of the same effect. So we name it as transpose underscore tab. That's actually the B matrix. So here we are loading the A matrix, we are loading the transposed version of the D matrix, and then we do matrix, we multiply them together. And we put the sum in the accumulator, and sum them up together. So this is the value. We do another add to put the value back to the accumulator. So this is the Intel version. The ARM version is actually very similar to the Intel version. So here we initialize this accumulator. So 4 entries, each entry is 32 bits. And then we load the A vector, load quad word, load B transpose, doing the multiplication, and put the sum to a vector add and put it in the accumulator. And since the accumulator is also 128 bits, it contains 4 entries. We're adding each entry 1 by 1. So in order to get the final C result, we have to accumulate the 4 entries to reduce these 4 entries into a single entry that becomes the CIJ. So from here we can tell the accumulator actually has 4 components, and we are doing them in parallel. Okay, so these are some very practical example how to accelerate the matrix multiplication using the SIMD instruction. All right, any question for the code here? We're going to see them in Lab 5, so make sure you understand each component very deeply. Right, so far so good. Okay, so let's jump into the next technique, which is multi-threading, concurrent execution of multiple threads within a single process. So let's compare a single thread versus multi-thread. Okay, so a thread is the smallest unit of execution in a program. So in a single thread case, they have the code segment, data segment, several open files, registers, and stack. But when you have multiple threads, they share the code and data. They share the code and data and also the file. But each thread can have its own register and also its own stack. Okay, meaning that it also have its own program counter. So different threads, they can run on separate CPU cores. And also when one thread is blocked, for example, by disk access or IO access, other threads, even on the same CPU, on the same resource, they can get unblocked and try to avoid such blocking. Okay, so that's improving the performance by using multiple threads to execute the task simultaneously, and also improve the responsiveness to make it responsive to user without blocking, and improve the resource utilization. If one thread is blocked, the other threads can continue. For example, in this example, the web serving is accepting the request, providing service to client 1, 2, 3, and across different timestamp, we can serve different users, allocate the thread allocated to the CPU. And sometimes they are sleeping while we are serving client 3. And when sleeping, this thread can serve client 2. When this can also get context switched to serve a different client. So we are utilizing the available resource very well, since not all the time client 1, 2, 3 needs serving. When client 2 doesn't is idle, we can serve client 1 or client 3 in this case. So very 2 practical libraries for writing multi-thread programs. One is pthread, the other is OpenMP. And let's see how do we speed up matrix multiplication using pthread first. So here we have A, B, and C. And remember, by using multi-threading, we have to block the matrix into several parts. Okay, each thread is responsible for several rows, the distinct rows in the A matrix. For example, thread 0 is only responsible for the first couple of rows. Thread 1 is responsible for the second chunk, etc. In this way, we can easily parallelize that, since the result of the first thread using this first small part of the matrix times the entire B matrix, what do we get? We get the first couple of rows in the C matrix. So are there any interactions between the threads? No, that's exactly what we want, to reduce the communication between the threads and make their workload as independent as possible. Like thread 1 works on this blue part of the input, multiplied with the B matrix, the entire B matrix, we get a blue part of this output. There's no interaction between the input output for the thread 0 and also thread 1, which is good case. So here we have 2 pieces of code. So the first one is calling the second one mathmal multi-threading. Okay, so let's see the first pieces of code. We first create the threads and assign the work. Okay, so we define thread data and define it by the number of threads. And we give it a amount of, we create these threads, typing in the pointer for the thread, and also typing each thread, what is the workload that each thread should do. This is a function name for the workload, like typing each thread, this is the work you should do. And then for each thread, we want to make sure they finish at the same time so that we can collect the final result. So we join the threads to wait for their completion. So we go through all the threads and make sure they all finished their task. And then we can return 0, telling the function that everything has completed. Feel free to access this matrix. Even if one of them hasn't finished, we cannot proceed. Otherwise, the data will be garbage. And let's see, what does each thread do? So it's the function right now body threading called here. And each thread is going to read its thread ID, and it's going to access the corresponding data using the thread ID. Like the start row would be start ID times the rows per thread. End row would be thread ID plus 1 times the rows per thread. Okay, for example, this is the start row, this is the end row, right? So we are going to use the thread ID to uniquely define the chunk of workload each thread need to do. And after having the start row and end row, it's going to do the matrix multiplication. So IJK 3 loops. I is from start row to end row. Yeah, it's just going to do the work 3 for loops as usual. So comparing the naive implementation of the CPU as a single thread, 24,000 milliseconds, multi-threading using 4 threads can have 4.1x speed up, a little more speed up, maybe due to better memory locality. So that's pretty easy to implement. We have the code in the same repo. Feel free to try it using the link right here. If that seems a bit complicated, there's an even simpler library for us. It's called OpenMP. Okay, Open Multiprocessing. You can have the API in C, C++, and also the Fortran, a shared memory parallel computing model, very portable. You write the same piece of code, no matter if it is what kind of processor it is, it's very portable, easy to integrate. You don't have to distinguish between like ARM version versus Intel version, right? It gives you several compiler directives like pragma OMP parallel to create a parallel region, and pragma OMP4 to parallelize a for loop, and also define the parallel sections. And also we can define those barriers, those single critical and barriers, and also get the number of threads, those kind of interfaces. And using those interfaces, we can very easily write parallel programs. So just just 2 lines of code can immediately turn your non-parallel code into parallel code. So we are parallelizing again for the A matrix in the row manner for the A, and also for the C. Different thread is doing a different chunk of the rows. So we just first set the number of threads to be 4 in this case by calling OMP set number of threads 4 to indicate the number of threads. And then we use the pragma to indicate where to parallelize. So here, which row, which for loop are we parallelizing? This I, K, this is J. So actually, we are parallelizing in the I dimension, right? In the I dimension. Therefore, we put the pragma OMP parallel 4 on top of its I dimension. So this I dimension just automatically get parallelized by 4 in this case. And that's it. And the code using OpenMP is much cleaner than that of using the P threads. Very easy to integrate with existing code. Like, for example, you wrote the existing code, you define ABC, you define the 3 for loops. And what you need to do is only 2 lines of code, set the number of threads, and also define which for loop you want to parallelize. All right, so after multi-threading, let's for the thread level parallelism. Let's talk about the CUDA programming, okay, using GPUs to accelerate the computing. We have worked on 3 labs, and all these 3 labs, you may have experienced the speed difference if you use the CPU in the Colab versus using the GPU on the Colab. So the GPU provide a much higher instruction throughput and memory bandwidth. And CUDA is the programming model introduced by NVIDIA more than a decade ago, almost 2 decades ago. And it has very good backward compatibility, making it a very advanced programming model for NVIDIA GPUs, making it super helpful for this AI computing, accelerated AI computing. It is C-like language to express programs that run on GPUs as if you are having that locally, right? So very easy to interface with the GPUs. Over the years, many generations of the GPU, but you can use the same programming model to program them. So let's first introduce what are the threads in the GPUs. So for example, here is it's a program. Okay, we can define the number of thread per block, and also the number of blocks. So basically, we have 2 levels of resource. So the grid can have many different blocks, and each block can have different threads. And we can launch these 2 levels of hierarchy of program by using in this way. Okay, so define the number of blocks and also the threads per block. Okay, so number of blocks and also the threads per block. In this case, the block is 2 by 3. The number of threads is 3 by 4. Okay, so altogether, how many threads do we have in this case? This is 6. This is 12. So altogether, we have 72 CUDA threads in this case. Okay, we launched the grid of 2 by 3, and each block we have 12 threads in this case. And here, nx, ny, they could be the dimension of the workload, the matrix, for example. And here we define the threads per block to be 4 by 3, and then the number of blocks can be naturally derived by 12 divided by the nx, which is 12 divided by 4, and also the ny, which is 6 divided by 3. So altogether, we launch 72 CUDA threads in this case. Okay, so there are 2 sets of code. One is running on the host, running on the CPU. The other is running on the GPU. Okay, so this is the host code running on the CPU, which is serial execution. What is responsible is basically allocate the memory for the matrix ABC, and also launch the CUDA threads. Okay, so here we bulk launch many CUDA threads. Actually, here we are launching 72, a grid of 72 CUDA threads in this case. Here we have 72. And this is the code actually running on the GPU. Okay, kernel code run the GPU device in parallel. So each thread is going to have this block ID and also the thread ID that's intrinsic to each thread. It knows its ID number. Remember, we have 2 levels of hierarchy. One is the block, the other is the thread. We have a certain number of blocks defined by dimension here, block dimension X, block dimension Y, and also a certain number of threads in each block. So the I and J will be defined by its block ID times the block dimension in X, and plus this thread ID. It's just like the multi-levels of array, we find the index, I wrote it in this way. And similarly for J, it's block ID in Y times the block dimension in Y, and plus the thread ID in Y. And for the thread ID and also the thread ID X and also the thread ID Y. Sorry, this thread ID for X and also the thread ID for the Y. They are intrinsic to each thread. So each thread is doing their workload according to their ID. Okay, and the workload they are doing is just AIJ plus BJI in this case. Okay, so uniquely identify your workload according to your index. So each thread computes its overall grid thread from its position in the block. So let's see the memory model. Previously, we are assuming this ABC are all allocated already, but let's see how are they allocated. So here we have the host, which is the CPU. In the PCIe, we have the device. Okay, we want to have two address space. One is the host CPU memory address space. The other is the device memory address space. They are distinct, and the data can be moved between the CPU and also the GPU. And we want to try to minimize those data movement. And here we are allocating a buffer in the CPU in the host memory. Okay, and we populate the host address space with pointer A. And here we call cooldown malloc to allocate the buffer in the device space in the GPU. Okay, so allocating GPU memory by calling cooldown malloc. And then we copy the data from the CPU to the GPU using this way. Can we access device AI from the host? The device A is addressed in the GPU memory. We cannot access the GPU memory in the host, in the CPU code segment.
What was the significance of the hierarchy? And how was in this example, how was it different from just having 72 threads from the launch from the host rather than having this hierarchy?
Yeah, so the more you have, the more threads have to be lockstep, but you don't have that large amount of parallelism. You are wasting a lot of threads. Now every 12 threads in this case have to execute the exact same thing. But if once you don't have that, so the hierarchy gives you this kind of a little bit of flexibility. Okay, so the memory model, okay, there are three distinct types of address spaces. Okay, so global memory, shared memory, and also the private memory. That also answers your question why we need the hierarchy. Similarly, for the memory hierarchy, we have the thread level. Each thread has its own private memory, and the block of threads have this shared memory. And finally, we have this global memory. And different address spaces, they have different overheads. You can imagine the private memory is the smallest, but fastest. The shared memory is larger. It's shared by each block, but it's larger but slower. So this is the matrix multiplication written in CUDA. So as we can see, we first allocate the memory for A, define the size of A and B, and also we do the workload according to the block ID for both the X and also for the Y. We can find the corresponding workload for the A, B, and C. And we wait for the memory loading. Okay, so make sure all the threads has finished loading the memory for a chunk of data. So make sure we have the good locality here. And finally, we do the accumulation by multiplying A and B together and storing it to the value. Finally, we wait for the multiplication and accumulation to finish across all the threads by calling this synchronize over the threads. And we can find the acceleration is pretty significant. on the CPU, it takes 25,000 milliseconds. On the GPU, the overall it's taken 258 milliseconds, like 100 times speed. But actually, the CUDA kernel is only 6.7 milliseconds. Among this 200 milliseconds, only 6 milliseconds is actually used on the actual workload on the GPU. The remaining is either the kernel call overhead or the data movement overhead. So actually, this is showing pretty exciting result for accelerated computing. From the CPU code to the GPU code, you can get orders of magnitude speed up. And recently, NVIDIA introduced this kind of tensor core, which further improved the speed up on tensor operations from Pascal to Turing from P16 in 8 to int 4, higher and higher throughput introduced in tensor cores. So this is the H100 flops per second, comparing the IP32, IP16, and also the TF32, and also int8, and also IP8. Actually, the 8-bit arithmetic is having a much higher throughput compared with the IP32 in the CUDA core. And this is our profiling result measured on A6000 GPU, doing the matrix multiplication by using the CUDA core versus using the tensor core. As we can see, the tensor core is up to 3.8 times faster compared with the CUDA core. So the tensor core offers this intrinsics to multiply a 16 by 16 times a 16 by 8 matrix using a single instruction. And this example is showing that we can work on larger workload matrix multiplication using this matrix multiplication intrinsics. We have a larger workload like 16 by 32 matrix, okay, and then followed by a 32 by 16 matrix. But using the intrinsic, which is 16 by 16 times 16 by 8, and we can do tiling like we learned before. Calculate the first part, accumulate and the second part, and accumulate, and finally we compute on a larger matrix using a smaller matrix multiplication intrinsics. All right, finally, let's talk about a few inference optimization techniques. First is image to column convolution. Like we mentioned, matrix multiplication is very well optimized. So can we do convolution using matrix multiplication kernels? Actually, we can definitely do that. For example, this is 9 elements in the activation, 9 elements in the kernel. We can flatten them. Okay, so that from A, B, C, D, F, G, H, I, J, K, L, M, we can flatten them in the row of one matrix, and we can flatten the kernel. And we have different kernels. There's 9 elements in the kernel. This is kernel 0, and then kernel 1. We can put them together. So in that way, we can flatten both the activation and also the weight into a same row and into one row and one column, so that we can do matrix multiplication to achieve convolution. And here the reduction is in the dimension of k squared c channel, and k is like 3 by 3. Okay, and finally we get a dimension of hw times m. What is the advantage? We can utilize the well-optimized GMM for convolution, but the con is that there is additional memory usage. For example, here, A and B appear here. When we are moving the window by 1, we actually have B, C, D, G, H, L, G, H, I, and L, and N. Actually, we are having 2/3 of duplicated memory, like you can see here. Lots of them are actually duplicated. So that's one of the cons. That actually can be solved by using on-the-fly computation rather than materialize everything S matrix. The next one is in-place depth-wise convolution. So we've introduced depth-wise convolution in inverted bottleneck layers, and each channel is operating independently. So previously, the memory consumption is 2 times CHW, since we have 2 copies, input and output. A very easy optimization is 1 plus C times HW, since we can do in place, have a temporary buffer, do the convolution locally, and then write it back, and then calculate the second channel. Since each channel they are independent, we can use this buffer where we are calculating different channels. So the memory footprint will be 1 plus C rather than 2C times HW. And also for the data layout, we can either have NHWC or NCHW. So this is the input activation. This is H and W and the number of channels. If using the NCHW, N is the batch, C is the channel, H and W is the height and width, we'll lay it out in this way. But NHWC, C becomes the inner channel. So in the memory, we are actually storing them in this way. Channel goes first. They can have an advantage in different scenarios. Okay, so for example, here, this is the pattern for NCHW. And here is the NHWC. If you are doing 1-by-1 convolution, apparently this NHWC is better, since the memory access is continuous, since we are doing convolution in this way. So this is point-wise convolution. What about depth-wise convolution? Actually, the result is different, since each channel is independent, right? So if we're using the NHWC format, 00001, corresponding to the first kernel, they are actually not contiguous in the memory, which is pretty bad. And then we go back to the second kernel, the right kernel. But if we are using NCHW, we are storing in this way. All the colors, they are contiguous, staying together, which is good. Which is showing that for depth-wise and also point-wise convolution, different formats are preferred for different kind of convolution. And finally, a magic convolution, which is called Winograd convolution. What is it doing is that rather than conventionally, we are doing convolution in this way, moving the input, moving the output. How many multiplications do we need to calculate 4 outputs? Each output we need 3 by 3 times C. So 9C for each output. We have 4 outputs, so that's 36 outputs. Max 36 max for 4 outputs. What Winograd convolution is saying that the input tensor will do a very simple data transformation that can be achieved by using just shift operation. And similarly, we do a filter transformation to get a transformed filter. Okay, we can do this offline, so that since this is a constant, right? And here we just do element-wise product over the C channel, which give you only 16 times C multiplications. So 16 times C compared with 36C, so that's 2.25x fewer number of max. And finally, we do an output transformation, which is again just shift operations. We can get the final 2x2 output tensor. So this is the filter. This is the input activation. We do such transpose using this magic matrix. And what does that look like? G just 0, 1, minus 1.5, minus 1.5, which can be all be implemented using shift operation. This is G transpose. Similarly, for the data transformation, B transpose only +1, -1, or 0. Very easy to implement in hardware. And finally, we have this output transformation consists of just +1, -1, and also zeros. So given this filter, we do such transformation offline, since the filter, the weight are static. And we can do this input transformation online, but luckily the transformation matrix is just +1, -1, so no multiplication is needed at all. So this is very commonly used technique to accelerate convolution during inference time. All right, we put them together and open source MCUNet and also TinyEngine for you to try it on the microcontroller, which was the homework last year. But this year we upgraded the homework to implement large language model on the laptop, which is pretty cool. So lab 4, we are going to do quantization for large language model, which is going to be released this Thursday. And in lab 5, we'll deploy it using the TinyEngine engine, which we give you a very good starter code, the baseline code, and your job is to make it run faster on your laptop. All right, that's all for today's lecture. We just learned Edge AI and parallel computing techniques, and also inference optimizations. All right, see you on Thursday.